Alright, welcome back everybody. In this video we're going to look at example 3 from the Substitution Part 2 lesson. In this particular example we're going to look at finding a bunch of integrals that look fairly similar and some of the differences that crop up as we find these integrals using substitution. So just take a glance quickly at all 4 of these integrals that we're finding. We've got 3 over the quantity 5y plus 4, and 3y over the quantity 5y squared plus 4, and 3y over the quantity 5y squared plus 4, the quantity squared, and 3 over the quantity 5y squared plus 4. All of these look fairly similar, but they're all going to be reasonably different in how we find these particular integrals. So let's go ahead and get started. We'll look at part A. We're finding the integral of 3 over the quantity 5y plus 4 dy. So looking at this, my first thought for substitution, usually we're looking for things that are inside of composite functions, and frequently a good substitution is the denominator of a fraction. It's not always our best substitution, but very frequently a good substitution for us is the denominator of a fraction. So for this one, I'm going to make my denominator my substitution, and we'll see what happens. We've got u equals 5y plus 4, and so du is equal to 5 dy. What I have left when I make that substitution is a 3 dy, so I'm going to replace the 3 dy with a 3/5 du, and this one rolls out pretty simply from there. It turns into 3/5 times the integral of du over u. And the integral of du over u is going to be the natural log of the absolute value of u. Straightforward antiderivative. And then I need to bring u back. And so I've got 3/5 natural log of the absolute value of 5y plus 4 plus c. And there's my integral for part A. Not too terrible. Alright, I'm going to apply the same kind of technique in part B. I'm going to just go ahead and substitute the denominator of the fraction, 5y squared plus 4. And so u is equal to 5y squared plus 4. And then du is equal to 10y dy. But I want to replace a 3y dy, so I'm just going to multiply both sides by 3/10 here. And I'm going to replace the 3y dy with a 3/10 du, and so this turns into 3/10 times the integral of du over u. And so again, I take the antiderivative of du over u. That's just going to be natural log of the absolute value of u plus c. And then I bring u back. So we've got 3/10 natural log of the absolute value of 5y squared plus 4 plus c. And in reality here, the absolute value signs are unnecessary because the quantity 5y squared plus 4 is always going to be positive, and so I could write my integral as this instead. Okay, so far so good. Not too bad. We picked the denominator in both cases. It worked out nicely for us in both cases. We ended up with these natural logs, and we're good to go. In part C, we're going to use a similar strategy. Instead of substituting the entire denominator, we're going to substitute what's being raised to the second power in the denominator. So again, we're going to substitute u equals 5y squared plus 4. And then du is going to be equal to 10y dy, and 3y dy is going to be equal to 3/10 du. And so this again turns into 3/10 times the integral of du, only now in this case it's du over u squared. So in order to find the integral of this, since it's not u to the first power in the denominator, we're going to use the power rule in reverse. This is really 3/10 times the integral of u to the negative second du. So it's going to turn into 3/10 times power rule in reverse, go up a power, divide by that power. And so it turns into negative 3 over 10 u plus c. And bringing u back, we've got negative 3 over 10 times the quantity 5y squared plus 4 plus c. So far so good. We did good by just substituting things that were in the denominator, and everything worked out fine for us. And D is where this concept kind of goes bad for us. So I'm going to show you what can go bad, or what looks bad, before we look at how we're going to actually approach this. If I tried to approach part D like I have all of the others, I would try to approach it by taking u equals 5y squared plus 4. And then du would be equal to 10y dy. Now if I tried to make this substitution, I'm trying to replace a 3 dy, and my problem here is that if I did that, or tried to do that, I still have a y here in the expression that I would be replacing 3 dy with. And so it's impossible for me in this fashion to replace this 3 dy with with this particular substitution, because I'll still have a y inside of my integrand, and in order to integrate it I need it to be strictly in terms of u and du. So this is going to be one that we need to understand and recognize how to approach it. Whenever we have a constant in the numerator and then some quantity where it's of the form ay squared plus b, or ax squared plus b, constant in the numerator, ay squared plus b, we're going to take a different approach to this substitution. Our goal is to turn this substitution into one where it ends up being something over u squared plus 1. Because when we have some constant over u squared plus 1, we can integrate that by using the arctangent function. The arctangent function is the integral of du over u squared plus 1. So we want to turn this into that form. In order to do that, let's think about what has to happen. We need y squared to be equal to 4/5 of u squared. Now why did we pick 4/5? Well, if we take this expression right here, the 5y squared plus 4, and we replace y squared with 4/5 u squared, it turns into 4u squared plus 4, which we can factor a 4 out of. And then we've got a u squared plus 1. Okay? So we want to replace y squared with 4/5 u squared. So let's see. Let's figure out what our substitution is going to be. That means that u squared is equal to 5/4 y squared. And so taking the square root of both sides, u is equal to the square root of 5 over 2 y. Dy, would be nice to know what dy is. Du is equal to then the square root of 5 over 2 dy, or dy is equal to 2 over the square root of 5 du. And so I've got all this information that I've splashed over here, and that's going to help me make this substitution. First, I'm going to replace, I'm going to bring the 3 out in front. I'm going to replace dy exactly with what it's equal to, 2 over the square root of 5. So I'm going to bring that 2 over the square root of 5 out in front and just put a du in there. So that gives me 6 over the root of 5 du. And now by replacing y squared with 4/5 u squared, I already did that replacement up here. That's 4 times the quantity u squared plus 1. Bringing the 4 out in front, I now have 3 over 2 root 5 times the integral of du over u squared plus 1. And I can find the integral of du over u squared plus 1 by just using the arctangent function. And so that's going to be the arctangent of u plus c. And then I bring u back. And u was equal to the square root of 5 over 2y. Got that right there. And there's our integral. So wow, part D of this example couldn't have been more different from parts A, B, and C than it actually was. And these are really complicated, or fairly complicated for integrals that we're going to take. You've got to be on the lookout. Anytime you see something of this form right here, constant over, ay squared plus b, you want to turn it into constant over the quantity u squared plus 1 through your substitution. These are some of the harder substitution problems that I've seen for students. You need to recognize and know this approach in case you run into something like this. Alright, that's the end of this video. We'll come back next time and look at the remaining examples from the Substitution Part 2 lesson. See you guys then. Have a great rest of your day.